Hi, in this lesson we will continue answering the questions about the diffraction. The first question, which one produces the widest diffraction pattern? Orange light, green light, yellow light, blue light. So when questions about the widest diffraction pattern or interference pattern, better to use the equation for sine theta. Remember, this sine theta was equal to m times lambda. So divide by the both side. So the sine theta is going to be m lambda divided by d. Yani the width of the pattern, which is represented by theta. Yani as theta increases, width of the pattern increases. So then the factors which increases the theta is going to increase the diffraction pattern width as well. So in here lights are given, so we know every different light has a different wavelength. Orange light, green light, yellow and blue light. So from violet to red, we know that wavelength increases. So of course the one which is closer to the in color to the red is going to have the longest wavelength in here. Orange light is closest to the length, so from violet to the red, so orange light is closest to the red. That's why orange light has the longest wavelength. If orange light has the longest wavelength, so theta, sine theta for orange light is going to be the greatest. That's why it's going to produce the widest diffraction pattern. And also you can answer this question by this way. We know that the light which has longer wavelength diffracts the most. The light which shortest wavelength diffracts the least. You can also go that way. So orange light has the longest wavelength, so it diffracts the most. Question number 2. A light shines at a diffraction grating that contains 3,550 lines per centimeter. The first order bright fringe make an angle of 12.07 degrees. What is the wavelength? So we are going to use again diffraction grating equations. This sine theta is equal to, which is m times lambda. So we will calculate this time wavelength. So we have to let lambda alone. Lambda is going to be the sine theta divided by m. So first we should calculate the this is the number of lines in centimeters. So from this information we can get d is equal to this tells you that there are in 1 centimeter there are 3,550 lines. So if we divide 1 centimeter by 3,550 lines, we will get the slit spacing. But I'm going to calculate slit spacing not in centimeter, in meter. That's why 1 centimeter is equal to 0.01 meter. So I will write numerator 0.01 meter divided by number of lines in 1 centimeter, which is 0.01 meter, 3,550. So this equation, this calculation will give me that the slit spacing for this diffraction grating 0.01 divided by 3,550, which is 2.8 times 10 to the power of -6 meter. So that is slit spacing. Then we can now calculate lambda. M is 1 because first order bright fringe, M is 1. No need to write M, has no effect in the multiplication or division. So lambda is going to be d sine theta, d 2.8 times 10 to the power of -6 times sine theta, sine of 12.07 degrees. So multiply this number by sine of 12.07, which is going to be lambda 5.89 times 10 to the power of -7 meters. So this is in meter, but choices are given in nanometer. I have to convert meter to nanometer. We can convert meter to nanometer by multiplying 10 to the power of 9, and you will multiply meter, which is 589 times 10 to the power -7 meter by 10 to the power of 9, and so you will get the result as nanometer. So in this case, the result is going to 589 nanometer. meters. So A is the correct answer. Question number 3. A grating with a 1555 lines per centimeter is illuminated with light of 565 nanometer. This time wavelength is given. What is the highest order number that can be observed with this grating? So remember that sin theta can never be greater than 1 for diffraction grating. So highest order number means we will find the greatest m. So I will write the equation again. V sin theta is equal to m lambda. We know that. We know that sin theta can never be greater than 1. And sin theta is always less or equal to 1. I will write it like this. Sin theta is equal to m lambda divided by d. So if sin theta is less or equal to 1, so m lambda over d also must be less or equal to 1. So I will continue with this way. So m lambda over d must be less or equal to 1. This is how we will calculate the m. If I got this, let m alone, m is going to be less or equal to d over lambda, because I will get d in here in numerator, lambda is denominator by cross product. M is going to be less or equal to d over lambda. Now, d must be calculated first. As you see, d is given in 1555 lines per centimeter. Let's calculate d again. I will calculate it in meter, in 1 centimeter, which is 0.01 meter. How many lines are there? Which is 1555 lines. Now let's calculate d. 0.01 divided by 1555. Result is going to be, d is going to be 6.43 times 10 to the power of negative 6 meter. I have to convert it to nanometer because wavelength is given in nanometer. So d is going to be, if I use this, multiply this number by 10 to the power of 9, result is going to be 31 nanometer. Now I can use d in here and then the lambda in here for calculating m. M is less or equal to d over lambda. D is 6,431 nanometer divided by lambda in nanometer 565. It is given in the question. So divided by 565, result is going to be 11.4. So m must be less or equal to 11.4. And of course m is integer. The smallest closest integer which is less than 11.4 is 11. So in this case m must be equal to 11. 11 maximum highest order number that can be observed with this grating is 11. This is the correct answer. Question number 4. All the points on a wavefront of a plane wave can be treated as a point source that each of these point sources produces a circular or spherical secondary wave called wavelet. This principle is called Huygens principle. This is defined in this book in details. Question number 5. If the number of lines per unit length of a diffraction grating increases, which means, remember, number of lines per centimeter I will indicate by n. If n increases, separation between the slits decreases, because we know that separation between the slits, the slit spacing, which is represented by 1 over n. If number of lines per unit length increases, then d and n are inversely proportional, d decreases. And distance between the individual fringe, yani angle, in fact, distance between individual fringes changes with the angle. As angle increases, distance between the fringe also increases. And how sin theta changes? Questions, in fact, asking this to you. So we know the sin theta equation, which is m lambda over d. So as number of lines per unit length increases, slit spacing d decreases, If d decreases, theta must increase, which is slits, the separation between the individual fringes increases. So answer is going to be B. And question number 6. For a diffraction grating, d is 2 times 10 to the power negative 6 meter. What is the number of lines per centimeter? I will use reverse. Remember, d is calculated by 1 over n. This time d is given, n will be calculated cross product. So when we cross product, n is going to be 1 over d. D is given in meter, but answer is given how many lines in centimeter. So I will first convert d to centimeter. D is equal to 2 times 10 to the power of negative 6 meter. So to convert to centimeter, I have to multiply it by 10 to the power of 2, because 1 meter is equal to 100 centimeter, 10 to the power of 2. D is going to be, in this case, 2 times 10 to the power of negative 4 centimeter. Now we can calculate number of lines per centimeter. So n is equal to 1 over bracket 2 times 10 to the power of negative 4 centimeter. So 1 divided by bracket 2 times 10 to the power of negative 4. Answer is 5,000. So number of lines per centimeter is 5,000. There are 5,000 lines in centimeter, because this is centimeter. So B is the correct answer. In the diffraction grating, which of these relation is correct between the number of lines and the slit spacing? In fact, we just get this equation several times. We use this equation. D is equal to 1 over n. N is number of lines, so 1 over number of lines is going to be the equation for calculating slit spacing. And question number 8. A diffraction grating contains 5,000 lines per centimeter. What is the slit space between every 2 adjacent lines of the grating? And slit spacing is the question. Again, there is the question in here. So we will calculate the result in centimeter. That's why we have to use centimeter. D is equal to, in 1 centimeter, there are 4,000 lines. So 1 divided by 4,000, which is 2.5. 2.5 times 10 to the power of negative 4 centimeter. Yeah. If the choices are given in meter, you should convert centimeter to meter in here, or as 0.01 meter. You should go that way, but as you see, choices are given in centimeter. That's why we don't need to convert centimeter to meter. So we should continue by centimeter. Which of the following objects would produce the most distinct noticeable diffraction pattern? So for most distinct yani noticeable, there are 2 quantities which affect this noticeability or distinctability. One of them is wavelength must be longer wavelength. If you compare the 2 lights, which one produces the most distinct diffraction pattern? Of course, the longest wavelength light. But second one is size of the object, because light is passing around an object. So wavelength must be longer to produce a most distinct diffraction pattern, or size of the object must be the smallest size. So now check which object has the smallest size in here. An apple, a pencil lead, human hair. Diffraction is the same for all of them. So human hair has the smallest size in here, so it produces the most distinct diffraction pattern. Question number 10. For a diffraction grating, the 2 micrometer, find the number of lines per centimeter. So per centimeter is the question. So that's why micrometer must be first converted to centimeter. D is equal to 2 micrometer. 2 micrometer, first let's convert it to meter by multiplying 10 to the power of negative 6. Now we converted it from micrometer to meter. From meter to centimeter, we have to multiply by 10 to the power of 2. So D is going to be, in this case, 2 times 10 to the power of negative 4 centimeter. And now number of lines per centimeter n is equal to 1 over d. So 1 over d is 2 times 10 to the power of negative 4. So use the calculator. 1 divided by 2 times 10 to the, so we should use bracket, 2 times 10 to the power of negative 4. Negative 4, close the bracket. Result is 5,000. So 5,000 lines, there are 5,000 lines per centimeter, so B is the correct answer. And question number 11, why is the diffraction of the sound easier to observe than diffraction of the visible light? In fact, answer is in here. Just we give that for most distinct or most noticeable diffraction, we need longest wavelength. So which one has longest wavelength, sound or light? Of course, sound has longer wavelength compared to the light. Light has very smaller wavelength, shorter wavelength. Sound waves are easier to detect than visible light waves, so that's not the answer. Sound waves have longer wavelengths than visible light waves, so they bend more around the bodies. So this is the correct answer. B is the correct answer. C. Sound waves are longitudinal waves which diffracts more than transverse. No, there is no relation about the diffraction being longitudinal transverse. All waves diffract. Sound waves have greater amplitude than visible light. That is not the case. Answer is B. Sound waves have longer wavelengths than visible light. That's why they deflect more or bends more around the barriers. Question number 12. According to blah blah principle, any point on a light wavefront can be treated as a point source of the wave. This principle is called Huygens principle. So this is all about the diffraction.